if you go on Google Earth, this is right about the area right here where I believe I was when I took that picture. Looking across, it's only about 0.6 of a mile. So I'm just a little over a half mile away, and look at the size of the tower as compared to the car that was diagonally in front of me. We were looking at the Willis Tower from this direction right here when we were on the other side of the lake. Now, okay, so let me slide the car over and shrink it down to the appropriate scale beside the boat. Do you see something rather interesting here? This building is significantly magnified. The image on the left shows the size and scale of the building next to a car at 0.6 of a mile away. The image on the right shows the same building and the same car with a boat at 46 miles away. The atmosphere really is acting like a lens. What type of lens? A convex lens or a magnifying glass. And let's just go back and hear from the experts once again what's happening with the atmosphere.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
Science is all about testable, observable, and repeatable data, right? So to alleviate the problem of distorting the edges because the magnifying glass ring is too small, I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
the atmosphere really is acting like a lens.
Yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. You're missing, a good portion of the city just by pulling my iPhone back on a 3-foot long desk. That's how much I lost of the city. We're all the way up against the glass. Now let's zoom across the lake, and wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. And this, of course, is my answer to the meme that you've all seen being passed around on Facebook showing the missing part of buildings is absolute proof of the curve. No, not really. But, okay, here's the part I really wanted to show you guys. I was already in the process of modifying my experiment, so here's what I came up with. I've got my magnifying sheet frame, and I created a little stand to paste the sun on it and keep it the same height over the flat surface of a table. So the sun is always going to be parallel with the surface. And check this out. All right, here's the first test of a sun moving over a flat surface. And with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface. As it was moving parallel, the same height, the whole way over a flat surface, the refraction caused the sun to set. Not only that, well, let's bring in the beginning of that. little test, and we see that it maintained pretty much the same size too, pretty close. Uh, and of course that's because as it's moving away, the magnification is still taking place, and so even though the sun's further away than it was in the beginning of the test, the magnification basically preserved the same size, and the refraction made it set. Now, I'm just going to put forward a crazy idea for you to think about. And that is, if Rob Skiba could figure this out, I'm just going to go out on a limb here. I think it's quite possible that the creator of the cosmos could have figured out the same thing and engineered our beautiful sunsets, thanks to all that water he placed in our atmosphere. Just something to think about. So, if you've been following some of my other videos, I've been showing how I believe the sun and moon work over the flat Earth model, and taking advantage of the fact that the atmosphere is full of moisture and that it is acting like a lens. I've done a number of videos, and one of the questions that has come up a number of times actually is, how is it that the clouds can be lit from underneath? Now, in the spinning heliocentric globe model, it's essentially explained that as the Earth is rolling away from the sun, as it's spinning, it rolls such that the sun is at a much lower angle, and because of that angle, the sun is shining up, and the sun rays are hitting the bottom of the clouds. So when you show people the model of the sun going around in a parallel path above the circle of the Earth, they say, well, in that situation, the sun is above the clouds, and so how could it possibly illuminate the bottom of the clouds when it's doing that? So I decided to take up that challenge and see if I could figure that out based on what I had learned in my previous experiments. And so I got one of these stick-em-up LED lights. You kind of push the button, it's got 3 little LED lights inside. And I taped it up so only one of the LED lights is showing, and stuck it on a box and put it on the table with my trusty plastic lens set up here. And I took my stand that I was using for the sun and moon and just set it up right here on top of these little Tupperware things. And I was thinking, okay, so let's just say the bottom of this little stand here represents the bottom of the clouds. And so as you can see here, the light is way above, it's well above what would be the bottom of the clouds in this example. So let's see what happens. I turned off the lights and set my iPhone to record, and I'm showing myself here recording all of this with another camera, and I pulled the light back on the table, and watch what happens here. Ooh, check it out. There's that refraction taking place again. It's got the light. It made the sun set, first of all, below the horizon in this case. And let's just show, this is just the iPhone view. I'm going to bring the cloud in here, and the platform represents the bottom of the clouds. So the sun's going down, and oop, there it is. The bottom of the clouds illuminated by a light source that's well above the clouds, moving parallel over a flat surface. So apparently it's possible for the sun to illuminate the bottom of the clouds even on the flat Earth model. I decided to repeat the test because science is all about observable, testable, repeatable observations, right? And this time, even though the previous test was done on a table with non-reflective tablecloth on it, I decided to take a piece of soundproofing that I had left over from when I was doing the audio drama for Seed the Series. And I even left the end curved up like this, so it really should prohibit any possibility of reflection bouncing off the table. But here we go again. Here's the same test, this time with soundproofing, lumpy soundproofing that would prevent any kind of reflection. And here we go. Oh, looky here. I got the exact same results. Huh.